Welcome to the next lecture of switching theory and logic design. In this class, we are going to discuss the concept of BCD to XS3 using PLDs. BCD to XS3 converter using PLDs. So here we are converting the BCD information into XS3, where the BCD information starting from 0 and ended with 9. So 0 to 9 characters from the BCD we are converting into XS3. So we know the conversion mechanism from BCD to XS3. So for the conversion mechanism we have to develop a converter. So that type of converter we are developing by using PLDs. So BCD to XS3 converter using PLDs is our next topic. Right. So before entering into the topic, first see the BCD to XS3 conversion table. So in this conversion table, so see here we have ABCD. These are the BCD values, that is binary coded to decimal values. Actually, these are the decimal values from 0 to 9. These are the decimal values from 0 to 9. And these 0 to 9 values were represented in binary. So this is the BCD information. This is the BCD information. So BCD data, binary coded decimal data, binary coded decimal data. This is the decimal data. So the binary coded decimal data is started from 0 and ended with 1001, that is 9. Next, coming to that, the equivalent XS3 information. So this is the XS3 information. Okay, for example, if you have 0, for the 0 equivalent XS3 number we have to write. So how we will get the XS3 number? Where XS3 number is equal to BCD plus 0011. That is nothing but as for BCD information you have to add 3. So the 0011 you have to add. So for example, if you need the 0 value in XS3, so you have to add 0 plus 3, that is equal to the final result 3. So 0 equivalent number in XS3 is equal to 3. So this is the representation. 0 plus 3 is equal to, that is the XS3 number. That is, in XS3 we are representing the 0 with 0011. For example, take any BCD value here. Take for example 3. Take an example of 3. Here, the 3 equivalent value in XS3 is equal to 3 plus 3, that is equal to 6. So 6 equivalent number 0100. So 0110. So see here, this is the equivalent representation in XS3. Actually, that value in binary or BCD is equal to 6, but that 6 we are representing in the XS3 code, that is with 3. So this is the 3 representation. Like we have 0 to 9 conversion. For example, take 9. 9 plus 3 is equal to 12. 12 equivalent binary value 1100. That 1100 we have represented here. This is the 1100 representation for 9. So the 9 value we are representing in XS3 as 1100. So this is the representation of binary to XS3 conversion. Next, coming to here, this XS3 code we can call as mirror code. The XS3 code we can call mirror code. Why? Because what is the first digit? 0011. What is the last digit? 1100. This is exactly reverse to the first value. First value and last value are both are reverse, right? So that is seems to like as when you in the mirror, when you raise your right hand in the mirror, it shows that is you lifted the left hand. Okay, exactly, it shows the opposite action like that. So the opposite value is this one. Next, coming to here, 0100. Here, that is 1011. That is exactly reverse value. 0101. Here it is 1010. 0110. 1001. 0111. 1000. So this is exactly reverse. This is exactly reverse to this value, and this is exactly reverse to this value, this one, and this is exactly reverse. This is reverse, and this is reverse. So like that, we have the reverse values. Okay, this is this type of code called mirror code. Our normal binary code we can call as mirror code, and this XS3 code also we can call mirror code. But BCD is not mirror code. Why? Because here the 0 value is 0, 0, 0, 0, and coming to the 9 value 1, 0, 0, 1. It's not mirroring, so this is not mirror code, right? This is you can call weighted code, but why? Because each combination 8, 4 to 1 or 5, 4 to 1 like that, we have the weightage for these numbers. But here it is non-weighted code. XS3 code is a mirror code, but it is not weighted code. Coming to the BCD code, this is weighted code, but it is not mirror code. So you have to remember these points. Now, we have to write down the BCD to XS3 conversion functions. That is, you have to write down E3, you have to write down E2, you have to write down E1, you have to write down E0. Where E0, you have to write down E3. E3 is equal to check that when the E3 value goes to 1, here C. So these are the zeros, and here 5, 6, 7, 8, 9. For 5, 6, 7, 8, 9, we have the 1 at the XS3 value for E3. That is sigma small m of 5, 6, 7, 8, 9. So these are the values for E3. Next, coming to the E2. E2 is equal to sigma small m of, so see here, 0. Here you have to take this one combination. This is 1, 2, 3, 4 and 9. So the values is 1, 2, 3, 4, 9. Next, E3. Where E3 is equal to, check here, 0 and 3, 4, 0, 3, 4, next 7, 8. So these are the values for E3. And coming to that, sorry, E1. This is the value for E1. Next, E0 is equal to sigma small m of, see there, 0, 2, 4, 6, 8. 0, 2, 4, 6, 8. So these are the values for, these are the minterms for the E0. So we have written E3, E2, E1, E0 Boolean expressions. So see here, now we are seeing the concept of BCD to XS3 Boolean functions. Just now we have completed the conversion table. From that conversion table we have written E3 is equal to sigma small m of 5, 6, 7, 8, 9, and E2 is equal to sigma small m of 1, 2, 3, 4, 9, and E1 is equal to sigma small m of 0, 3, 4, 7, 8, and see E0 is equal to sigma small m of 0, 2, 4, 6, 8. So these are the Boolean functions we have analyzed from this conversion table. From this conversion table, we have drawn this. We have written the four Boolean expressions for E3, E2, E1, E0 outputs. Okay, right. Now here our task is implementation of this BCD to XS3 code converter by using PROM, PLA, PAL. So these are the three devices are called PLDs, programmable logical devices. Okay, in that first we will implement this BCD to XS3 converter using PROM. BCD to XS3 converter using PROM. Right. So coming to that, before going to that, first you have to say what is PROM. PROM is programmable read-only memory. So this PROM generally we can call as ROM also, but in the ROM there is no chance of programming, but in the PROM we have the programming facility. So this is the programmable read-only memory. And coming to that, it consisting of two levels of logic gates. So that is fixed and array gates and programmable or array gates. So here in the we are giving the inputs to the fixed array of AND gates, and next we are this fixed and array outputs we are connecting to the programmable OR gates. So in the place of fixed and gate arrays, we are using decoders. So the decoder output we are connecting to the OR gates, a group of OR gates, where that OR gate inputs we can program. That is completely the user choice. The user, if he want, he can connect, otherwise he can neglect. This type of connectivity is called programmable read-only memory. The AND gates are fixed, we are taking in the form of decoder, and the OR gates we are representing as how many OR gates you require, those number of OR gates you have to draw here. So in this way we are taking the PROM structure. So generally ROM is used for reading the data from the ROM. Generally we will store the data on the ROM. at the industry side or from the vendor side. After writing the data on the row, we cannot erase. If it is programmable, we have some flexibility to change or to modify the data. Okay, so in the row, we can program for the OR gates. We cannot program for the AND gates. Right. Now, see here, the BCD access 3 using PROM. So first here, see here, when you are implementing this function, for here, you have AND gates. Right, that is with the help of decoder. The decoder has outputs of standard minterms. So for that reason, first you have to take the inputs of those functions. Okay, so see here, for implementing this BCD access 3 code, the BCD inputs are 4. For that reason, I need 4 input decoder. If I have 4 inputs for the decoder, the outputs are the 16 outputs. 4 to 16 outputs decoder we have to take here. 4 to 16 decoder here we have to take. So coming to here, in this 4 to 16 decoder, for the XS3, we are representing from 0 to 9. After 9, 10 to 15 we are not representing. So for that reason, 0 to 9 outputs I have drawn here, and from 10 to 15 I am not drawn here. So it's very simple diagram. So here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Totally 10 outputs are available. Where 0 is representing A bar, B bar, C bar, D bar. So the 0 is representing A bar, B bar, C bar, D bar. And 1 is representing A bar, B bar, C bar, D. A bar, B bar, C bar, D. And 2 is representing A bar, B bar, C, D bar. And 3 is representing A bar, B bar, C, D. Right? We are taking the values of 4 to 60 corner from here to here. Right. Now coming to here. So by taking these output lines, we have to construct E0, E1, E2, E3. So coming to here, here I have 4 outputs. So based on the room connectivity, I have taken 4 OR gates here. Those 4 OR gates are E0, E1, E2, E3. The first one E3, second one E2, the third one E1, and last one E0. Right. Coming to the E3 function. So what is the function there for the E3 that you have to bring here? So see here, the first we have E3, where E3 is equal to sigma small m of 5, 6, 7, 8, 9. So the 5 we have to represent here with a cross mark. The 5 we have to represent with a cross mark. So the 5 we have to represent with a cross mark for the E3. So we need the output at the E3 with 5, next 6, next 7, next 8, next 9. Okay, these 5 inputs are required for implementing the E3 output. Next, I need E2. Next, I need E2. So see here. So for the implementing E2, 1, 2, 3, 4, 9 I require. So see here, 1, 2, next 4, 3, 4, 9, 3, 4, 9. Okay, for E2 you have to take the decoder outputs, that is minterm values. That minterms I am taking like this, in this way. I am taking in this way. Next, coming to here, E1, where E1 is equal to 0, 3, 4, 7, 8. So 0, this is a 0, and this is 3, and 4, and 7, and 8. These are the outputs from the decoder, and these outputs we are connecting to inputs of an OR gate. Okay, next, that means the E1 is connected to all these AND gate outputs, that is from 0, 3, 4, 7, 8. Okay, next, coming to the E0, where E0 we are representing, where E0 is equal to sigma small m of 0, 2, 4, 6, 8. So this is 0, 2, 4, 6, 8. 0, 2, 4, 6, 8. Those outputs we have connected to the E0. Like in this way, from E3 to E0, all the outputs we have defined from the decoder outputs. The decoder output has ready-made min-term outputs. That is, the 4 to 16 decoder has 16 outputs. Each output is representing one AND gate output, where the AND gate is formed with 4 inputs of ABCD with a different combination, where 0 is representing A bar, B bar, C bar, D bar, where 15 is representing ABCD. But 10 to 15, we don't bother about that outputs. There is no necessity of those outputs. So for that reason, we have left them and we have taken whatever the min-terms are covered from the conversion table. From that conversion table, whatever the functionalities we have drawn or we have written in the form of Boolean function, those functions we have taken here. Okay, right. So this is the BCD to XS3 converter using programmable read-only memory. Next. Next coming to that, BCD to XS3 converter using programmable logical array, that is PLA. So first we have to see the programmable logical array structure. Where programmable logical array structure, we have to see what is the AND gates behavior and what about the OR gates behavior. So let us see the inputs, whatever the function has the inputs, that inputs we are giving to the programmable AND array, and this programmable AND array outputs we are connecting to the programmable OR array, and this programmable OR gate outputs we are connecting to the finalized outputs. Okay, right. So the AND array here we can program. That means whatever the inputs required, those inputs you can take, and how many number of AND gates you require, those number of AND gates you can take. That means you can take here 2 input AND gate. Otherwise you can take 3 input AND gate, otherwise you can take 4 input AND gate. That is up to you. So whichever the AND gate you require here, you can take here. And whichever the OR gate you require here, you can take. That is, the flexibility of the sizes of the AND gate OR gates is given to the user. Okay, that means we have a lot of information at a lot of AND gate arrays and OR gates are available in this programmable logic array chips. In the PLA chips, we have these AND gate OR gates. For these 2 gates, we can program. That is the major concept here. Right. Now coming to here, our next thing, first write down the functions, those who are taken from the conversion table. So these are the E3, E2, E1, E0. Here I said that I can take whichever the function I required here. So I don't want to take this much big number of functions here. Now I want to reduce these functions by using K-map. So for that reason, for E3, E2, E1, I have drawn the K-maps here and I have solved this problem. So for E3, I have drawn this K-map, where this K-map is consisting of, that is E3, 5, 6, 7, 8, 9. So these are the 5, 6, 7, 8, 9, and remaining 10 to 15 are the don't care combinations. Those by using those don't care combinations and by using those functions of min-terms. Okay, the min-terms which are defined in the function, that min-terms and don't care combinations I have taken here, and I have made one octogroup and 2 quad groups. From this I have written the expression where E3 is equal to A plus BC plus BD. A plus BC plus BD. Right. Now, right, coming to the E2, this is B bar D plus B bar C plus BC bar D bar. And next coming to that E1, so here we have formed 2 quads by using this functionality where E1 is equal to 0, 3, 4, 7, 8, 0, 3, 4, 7, 8. We have made 2 quad groups, and the final function E1 is equal to C bar, D bar plus CD. And coming to that E0, here for the E0, here we have framed an octogroup. That octogroup is representing D bar. So these are the finalized 3 functions for the BCD to XS3 converter. By using K-maps, we have obtained these 4 functions. Now, when you are implementing this BCD to XS3 code by using programmable logical array, here the number of AND gates and number of OR gates are completely programmable, that we can modify the number of inputs also. So for that reason we have taken the simplified expression. So here, before going to the draw about programmable logical array converter, so first identify how many number of AND gates here we have, how many number of OR gates here we have. So see here, A plus BC plus BD, here we have 2 AND gates. Why? Because for A there is no list of AND gate. For BC we need an AND gate, and BD we need an AND gate. And B bar D, next B bar C, next B C bar D, and C bar D bar CD. So these are the 1, 2, 3, 4, 5, 6, 7. Total 7 AND gates are required. Total 7 AND gates are required. In these 7 AND gates, 6 are 2 inputs and only one is the 3 input AND gate. So see here. So this is only 3 input AND gate. Remaining this one, this one, and this one, and this one, and this one, and this one. These 6 are 2 input AND gates only. Okay. So finally, these are the functions we have to implement by using programmable logical array. So those are all functions I have written there. Now here first we have to draw the programmable logical array. In this first level is AND gates. So for drawing this AND gates, you have to take the 4 inputs. So the 4 inputs and its complemented form, A, B, C, D, 4 inputs and complemented forms, A bar, B bar, C bar, D bar. So first I have taken, see here, A bar, B bar, C bar, D bar. So these are the 8 inputs. These are the 8 inputs. These 8 inputs lines I have drawn here. Right. From these 8 input lines, so here I have taken totally 7 AND gates. So the first one, 7 one, second, third, fourth, fifth, sixth, 7. Total 7 AND gates I have taken, and I have represented each gate with its combination BC, BD, B bar D, B bar C, B C bar D, and C bar D, and CD. And last one is D bar, and the first one is A. These are the total informations here we have to take. And next coming to that OR gate array, which is followed by this AND gate. So these are the OR gates. Totally we have 4 functions. For implementing those 4 functions, E3, E2, E1, E0 we have drawn here, we have written here, and for this OR gates we have make the connections with the AND gate outputs. Now here we have to program. So see here, I have programmed and I made the corrections, that programmable connections, where into is representing the programmable connection. The programmable connections wherever I required. So see here first A, B, C, B, D. So this is A, where A I have shorted here. From this line, this I have drawn the complete line. So this complete line is connected to this OR gate. That is, the E3 is connected to this line. This line is connected to the A signal. That is, the one of the OR gate input is equal to A. Next, second BC. So this is the B signal, this is the C signal. So this is B and this is C. So this AND gate gives the BC product, that is B into C. That BC line is also connected to this E3, connected to this E3. Next coming here, B and D. So this AND gate carries the B and D values. Why? Because here we have given a cross mark, where the cross mark is nothing but as there is an electrical contact between input line and AND gate input. So that is the information is connected to this BD. So that BD output is also connected to this E3, connected to this E3. So in this way we have implemented the E3 function. In the same way E2, B bar D, B bar C, and BC bar D bar. So here, so B bar C, B C bar D, C D. So this is B bar and this is C. That is B bar C. This is a product. And next B, C bar, D bar. So B and C bar and D bar. So these are the 3 inputs for this 3 input AND gate, and this is a C bar, D bar. So C bar, next G bar. So that is C bar, D bar. Next CD, C, D. So D value, C value. That is the next product term, and the final value D bar. This is the D bar. So all the AND gate terms are okay. And coming to the E2 function, where it is called B bar D. So the B bar D we have taken, and B bar C. The B bar C also we have taken here, and B, C bar, D bar. For this E2, the B bar, C bar, D bar also we have taken. The 3 inputs we have taken here. And E1, where E1 is equal to C bar, D bar plus CD. So C bar, D bar, CD. So see here, C bar, D bar, that's we have mentioned as down. So this is the connection we have made here, that is C bar, D bar and CD. These two connections are connected to this E1. So finally we have implemented E1 function, and where E0 is equal to D bar, this D bar is connected to this line. So see here, D bar is connected to this cross line is connected to E0. So in this way we have implemented the programmable logical array of BCD to XS3 and decoder or converter. So BCD to XS3 converter by using programmable logical array. This is the implementation part. Okay. Right. Next, coming to the BCD to XS3 converter by using programmable array logic, where programmable array logic has two arrays like as AND array and OR array, where the AND array is the programmable AND array and OR gate is the fixed OR gate array. So that is for the AND gates we can program. So here this is the has the facility of programming. So for that reason you can simplify the function. That is, you can use the minimized equations, and for fixed OR array gates you have to give the constant inputs for the all OR gates. For example, an OR gate is connected with 3 inputs, remaining all the OR gates also connect to 3 inputs. Otherwise, if an OR gate is connected with 5 inputs, remaining all the OR gates has also connected at least minimum number of 5 inputs. That is also defined by the vendor. So see here, so these are the minimized functions. These are the minimized functions we have taken in the previous K-map simplification process. So and these expressions has to develop here. So see here, the dot is representing the industry standard contact. This is the electrical contact given by the industry people. And E3, E2, even E0. Where E3 has 3 input connections and E2 has 3 input connections and E1 has 3 input connections and E0 has 3 input connections.Ese are the standard connections we have to take from the industry. So we don't have any choice to modify these connections. The 3 connections are fixed by the industry. Now at the inputs of AND gates you can modify whatever the connections you require. So here we have the AND gates A, B, C, B, D. The same expressions you can write here. So but you have to remember, right? So coming to here, we have to develop the AND gate inputs combinations here, but all the AND gates only here you have to use. This AND gate outputs you have to connect here. So each E3, E2, E1, E0, it has 3 input connections as per industry standards. Now take all the input combinations here. Now take the all input combination, that is A, B, C, B, D, B bar D, B bar C, B, C bar D. So these are all the combinations now you have to represent. So I have represented all the input combinations and I have written the which combination I have represented for this AND gate. So this is A. So one input AND gate, if you have given A, the output is also A. And if you have D input, that is also output as D. So from this AND gate, that OR gates are connected. So for that reason, if no signal or one signal is connected, then you have to go with the help of the AND gates. Okay, so which type of AND gate you require, that type of AND gate you can draw here, that you can use. But you have to represent each and everything with the AND gate help, with the help of AND gate only. Okay, so this is the finalized implementation by using programmable array logic of BCD to XS3 and converter. BCD to XS3 converter we have implemented by using programmable array logic. Right? So coming to that, finally, in this class we have learned about the BCD to XS3 using PROM, BCD to XS3 using PLA, BCD to XS3 using PAL. That is BCD to XS3 converter we have implemented by using all 3 types of PLDs. By using PROM, by using PLA, by using PAL, we have implemented. Okay, right. Thank you.